Okay, thank you. So I'm not going to try and point to one of the two screens. I don't think that really works very well. So I'm from Intel, and this is the first in a string of several sessions around persistent memory, and there's some non-volatile memory in there. I think we have maybe 4 or 5 sessions starting now. And we thought it would be a good idea to start with an overview of just persistent memory. What is it? How do you use it? So my part is mostly about just what it does and how you use it locally. And then in the next talk, Tom Talpe is going to talk about RDMA. And we actually have RDMA coming up in several of the following talks. So hopefully it all kind of holds together nicely, and you won't let the fact that you just got back from lunch let you sleep through this. But, we'll see. I won't hold it against you. So I thought I was cover, what is it? Why is everybody talking about it? Why are we interested in it? Is it really that interesting? How does the program use it? What are the challenges? And then finally, I'll give you the current state of the ecosystem. Okay, so starting out at the very beginning, what is it? Well, this is kind of a marketing-ish slide. I borrowed this from marketing. I'm not in marketing. But this is just kind of pointing out that we've had this increase over time in the bandwidth of these devices, starting from hard drives to SSDs to now the PCIe connected SSDs. And of course, the latency has done the same sort of improving thing from hard drives to SSDs to PCIe SSDs. And you can see we're headed to this part in the middle where we suddenly get low enough latency and high enough bandwidth that the line between storage and memory is starting to blur a little bit. So as this started to come up about, I don't know, more than 5 years ago now, several of us got together, mostly started by a couple of us at Intel and a couple of people at HP, including Doug Voigt, who's sitting right over there. And we decided, wouldn't it be a shame if everybody decided the way that you use this is different on every OS and on every platform? And wouldn't it be a shame if you had to choose some vendors, private APIs and lock yourself into one vendor? So we formed this SNIA technical work group. SNIA is the Storage Network Industry Association. And one of the first things we had to do is define what persistent memory is. And so this is my definition of persistent memory. It mostly matches what we wrote into the SNIA document. Maybe this is a little less formal. But my definition of persistent memory is that it's byte addressable, at least as far as the programmer is concerned. Of course, the computer is free to, inside of its internal buses, it can do things in cache lines, which is the norm. But it's not demand paged, right? If you go and access 1 byte of persistent memory, you don't have to clear out something in DRAM and bring in a block from storage. It really is access in place. So it's load, store, access. And it has memory-like performance. And at first we started trying to say, okay, it ought to be this many nanoseconds to be considered persistent memory and so on. But there's so many ways of building something that acts like this. We decided that it was wrong for us to state specific performance values. Instead, I did this sort of, it's a little bit of hand-wavy, but it actually has worked out pretty well for us. It has to be fast enough that you would reasonably stall the CPU waiting for a load, right? In other words, if you're going to load something from persistent memory, it's okay just to wait, just to introduce a bubble in your CPU pipeline and wait for it, because unlike flash and hard drives, there really isn't time for you to context switch away, get some other work done, wait for the I/O to complete and context switch back, because the load is so fast. So it's a little bit of a subjective definition. And it sits on the memory bus, so probably DMA-able, probably RDMA-able. I'm going to say more about that. And so for modeling this, think about just a bunch of DRAM with a battery backing it. And in fact, that's how we developed all this software and everything until the DIM, this DIM that I've got a picture up on there, until that was available. So that's my definition of persistent memory. So why is that interesting? So what, right? What's so interesting about that? Well, I work for Intel, so I'm going to talk about the emerging technology coming out of Intel, but there are several companies talking about technologies like this. Ours is called 3D Crosspoint, actually developed in collaboration with Micron, and announced a couple years ago now at an IDF, an Intel Developer Forum in 2016. And It is, all those things I said before, it's persistent. It has fairly large capacity. It's byte addressable. What has been announced so far is that the capacity is 6 terabytes in the common 2-socket server, so 3 terabytes per socket. And you know, this is actually, I bolded the 6 terabytes here, because this is actually one of the exciting things about persistent memory to me. There's a capacity explosion here. It's pretty hard right now to build a 6 terabyte memory 2-socket system. I don't even know if it's possible. I think you'd have to have 2 56 gig DIMMs, DRAM DIMMs, which would, if available, would be very expensive. So that's pretty hard. So that's what's sort of exciting about this. There's this explosion in capacity. The technology goes into a DDR4 socket. I got a DIMM here. You guys can come look at it afterwards. Find me in the hallway or something. And so it can coexist with DDR4 DRAM DIMMs. We're now to the point, since the 2 years when we announced this, where we've now seen public demos on top of these DIMMs, on top of samples, basically. So it's getting closer to getting released. It's cheaper than DRAM. How much cheaper? I don't know, because I'm not in marketing. I wore my jeans to prove it. But it's cheaper than DRAM, and of course, the pricing information will be available when the DIMM is available later in 2018. So this is one of the emerging technologies that's kind of got us all excited about persistent memory. But again, so why is that exciting? So why that is exciting, this is a slide that is kind of a zoom in of the slide that we saw during the keynote, where you can see on the left bar there, this is the overall latency of if you just want to access, well, basically, if you just want to access 1 byte, you know, you just want to access 1 byte off of your storage. And so you get a nice fast SSD, an NVM Express SSD, and you do well, you can only do a 4K read. So you do a 4K read, and you can see the latency there is, I don't know, somewhere in the 90 microsecond range. And that big blue bar there is the media, right? That's the flash. So you can see the driver is that little tiny sliver of red on that bar, if you can see it. So, you know, I'm an OS guy, you know, a kernel guy. I'm going to make this faster. Should I go make the driver faster? I could double the performance of the driver. It wouldn't make a bit of difference because it's that big blue bar. That's really the problem. But now we have this 3D crosspoint stuff, so let's make an SSD out of that. That's the middle bar, and we call that Intel Optane drives. And so again, you can see now that blue bar has shrunk way down. So now we've really gotten the latency way down. And now actually the other parts, the software stack and the PCIe interconnect and so on, are now taking up more than half of the latency. The media is no longer the long pole in the tent, as they say. So that motivates us to say, okay, well, what if we just plugged it directly into the memory bus? And that gives us the bar on the right, where you can see the latency is really tiny. And in fact, that little tiny bar is the latency of a 64-byte read. That's something you're not really allowed to do with storage, but with memory, that's commonplace. So if you really just need to access 64 bytes, you don't have to transfer an entire block. You don't have to waste all that bandwidth. I did put the little white box there as a full 4K, just so no one could claim I'm not showing apples to apples. So that's why it's so exciting. It's exciting because, well, it's so fast that we now are motivated to plug it right into the memory bus. It's so big that it's bigger than any of the DRAM capacities that we could build right now. And so the value that we get from this is that we can access these large data sets that fit into persistent memory. They wouldn't fit into DRAM. And we can access them without paging, so we don't have to kick other things out of DRAM as we access them. So one of my favorite examples is you want to build a giant hash table for a dedupe for storage or something like that. Usually those lookups in those hash tables are pretty small. Same thing, a lot of hash tables like HBase and things like that. Those lookups are small, so you don't need to pull in big pages off of storage. You'd just be wasting bandwidth. But with persistent memory, you can just go and access it directly in its resting place in persistence. DMA and RDMA pretty much work as expected. We're going to talk about RDMA a little more in the rest of the talks here. If you don't care about persistence, they work exactly as expected. But RDMA was designed before there was persistent memory, or at least after there was persistent memory, if you think about the old core memory. So that's why RDMA doesn't currently comprehend it. You also get this warm cache effect, which is pretty interesting. So one of the values of persistent memory is that you can store an entire in-memory database in the persistent memory instead of DRAM. And after the system goes down and comes back up, it's still there. So instead of taking potentially hours to reload some huge database, you can be up in seconds. We've already talked about byte addressable, but also since it's byte addressable, you could imagine, and since it's memory, you could imagine giving this to applications for direct user access. So should we do that? Just because we can doesn't mean we should, right? Should we do that? That's really a good question. So when I started looking into this, I started thinking about where should it be transparent? There's always some level in the stack above which they have no idea you're using persistent memory, right? So how far up this stack should I go? I could just say only the driver knows that it's persistent memory. And the driver just takes the normal block read, block write interfaces and does copies to and from the persistent memory. That'll work great. No problem. No software has to change after that, just the driver. File system stays the same, app stays the same. I'm done. Piece of cake. But the farther up the stack you go, the harder it is for people to adopt this stuff because I start forcing them to modify their file systems and to modify their applications. On the other hand, the farther up the stack you go, it turns out, the more leverage you get out of this stuff, right? Storage APIs are based on buffers. You do a read or a write to a buffer. You pass a buffer in. There's a copy, no matter how you look at it, it's got to be a copy because it's a buffer that you're passing around. But if I can take APIs that are about accessing data in place and push them up to the application, I can get more leverage out of this. So as I go up the stack, more barrier to adoption, but also more leverage. It's a trade-off. Okay, so how did I do that? Well, I had a lot of help. And I went to, like I said, the SNIA technical working group that we formed, and lots of companies participated in that. Something like 40-something companies participated in that. And so we started off by saying, okay, well, what does the storage stack normally look like? At a 50,000-foot view, it looks like this. This is my common picture of a storage stack. There's storage at the bottom. There's a driver. There's a file system. Applications sometimes talk directly to the driver. Sometimes they talk through a file system. But this is the stack that should be, hopefully pretty familiar to everybody. It's just got, user space and kernel space components divided up here. And notice there's no mention of an OS. They all kind of look like this. There's slight differences, but they're all pretty much the same. And as I said, most people are used to, just to prove I'm an engineer, I put some C code on a slide here. Most people are used to doing this kind of read, write, syscall based I/O. Even if you've never used these system calls, you've used them, right? Because this is how a kernel is asked to initiate a read or a write. So if you're using some library that hides this from you, or some language that hides this from you, underneath it's still doing this, right? It's still calling into the kernel with read and write. And these are buffer based because they pass a buffer and a size. So no matter what, you're saying, okay, here's a spot in DRAM. I want you to initiate I/O to or from this DRAM. On the other hand, most OSs for at least 30 years have had this thing called memory mapped files. These are lesser known to a lot of people, although I suspect that people in this room all know about memory mapped files pretty well. But they're not as commonly used, especially on Windows. They're not that commonly used. On Linux, they tend to be a little more commonly used. They're often used incorrectly, but what can we do about that? So on Linux, the call is mmap. You pass all these arguments and you get back this pointer, which I've named base. And at that point, you can use base. It's a pointer to memory. See, I'm assigning X to it. Notice I closed the file descriptor, right? The file's not even open anymore because mmap is one of the few ways of getting something added to your address space, right? So you're getting something added to your address space. Well, where am I going with this? Well, persistent memory is accessed like memory. So I want to be able to add it to my address space so I can do things like stir copy to it or assign to it. And I call this load store access. But, for 30 years, this is paging, right? When I do these things and I start doing those accesses, the storage system, my process gets put to sleep, the storage system initiates an I/O. Finally, my process wakes up, and now it's actually messing around with the DRAM. Okay, but it doesn't have to work that way, right? I could just say, what if I defined a persistent memory-aware file system as one that's not going to do paging when I do this. It's not going to use the page cache. So we set out to do this, and we started out in both Windows and Linux with this idea that there's a persistent memory-aware file system, and it has a feature known as DAX. Actually, the features are named the same thing on Windows and Linux. DAX is short for direct access, and the definition of that feature is that there's no page cache. So, you can see open, close, read and write on that standard file API that I'm showing there. It just works the way you'd expect it to work. And if I stopped there, open, close, read and write would just work maybe a little faster because they can skip the block stack if they want to. They can go directly to the NVDIM. But the whole point here is that what happens when you mmap a file? You get the far right blue arrow when you mmap that file, and that gives you direct load store access. So on that far right blue arrow, an application has the shortest code path possible to persistence, right? It does a load instruction, and it loads directly from persistence. There's no kernel code. There's no interrupts. There's no context switching. It's literally one instruction, right? In fact, with prefetching, it's maybe slightly less than one instruction. So that's the exciting part. Of course, we'll find reasons why we want to add some code back in that path in a few slides. But it's nice to be able to start with something very raw like this as the base case. And you're welcome to program to it this way, right? It's a little bit like taking some poor programmer and saying, OK, here's 6 terabytes. Here's a pointer to 6 terabytes. Go to it. Have fun. The first thing that programmer is going to do is say, whoa, 6 terabytes. What am I supposed to do now? But again, some of the people in this room know exactly what to do with a pointer to 6 terabytes, right? Some of these HPC use cases, they don't need any help. This is it. They just want, give me access to the raw stuff. But remember, you can't mmap something without opening it. So you had to give it a name, and you had to have permissions to open it. And that's what I'm using the file system for. We did not want to introduce some new bizarre permission model or some new bizarre naming model for persistent memory. We wanted to leverage the decades of file system infrastructure that we have. So that's the basic programming model. Notice there's still the middle stack. The NVDIM driver there still does provide storage APIs. If you don't want to modify your application or your file system, you can use it in the middle stack, and it'll all just look like the world's fastest SSD. But those are block APIs, block interfaces. They're almost too easy, so I don't talk about them much. But they're there, and if you want to start using persistent memory immediately, that's how you do it. You don't have to modify your app. But if you want to fully leverage persistent memory, you want to move over onto the right-hand side and make changes to your application to use the load store. So what are the challenges? Gosh, it sounds so easy, right? Well, like I said, if you just hand somebody a pointer to 6 terabytes, the first thing they need is some sort of allocator. Can I just put malloc and free on top of that? I'm a C programmer. I know about malloc and free. Well, of course, the malloc and free libraries that you all know and use have volatile memory baked into them. In other words, they don't do anything to make sure that they're consistent across a crash. So if the program crashes in the middle of an allocation and you come back up and reconnect to that persistent memory, the heap is probably in some unknown state. It's probably has pointers that are invalid or maybe memory that's leaked. And the only thing worse than a memory leak is a persistent memory leak, right? So yeah, you need an allocator. You need a persistent memory-aware allocator. You want some sort of consistency across failure, some sort of transactional updates. You want your data structure, so if you build a big hash table or a big tree or something like that, you want to be able to make changes to it. And then if you crash or if your machine crashes, you want to come back and just reconnect it, roll back any half-done changes, and keep going. And things like DMA, can you receive a packet from the network right into persistence? Sure, that works. Can you do DMA to it? Sure. But RDMA, like I said, doesn't really comprehend persistence. So if you want to use RDMA to it, you might need an extra step to figure out how to get that done. Now, Tom's talk right after mine is going to go right into that, so I won't spend much time on it. For those of you who like to go down into the hardware and say, okay, well, how does this really work? I put this how the hardware works summary slide in here. And this is actually particularly interesting because it also gives you a glimpse of where I think we're going in the future. So A store is called a move instruction on Intel. You can see it in the upper left of the slide. It makes its way through the L1 and the L2 cache, the L3 cache. That trapezoid is the memory controller, which is integrated into our chipset, and it has its own set of queues in it. And then eventually it makes its way to the DIMM. So there's really two possible persistence domains here. In other words, two possible places where you can say, I consider this store to be persistent. One is the small red dashed box at the bottom. That includes the memory controller. That means once a store is received by the memory controller, you can consider it persistent because of a feature that we put in all of our platforms that support persistent memory that flushes those queues in the memory controller automatically if you lose power. Okay, so the important point here is you don't have to wait for the store to go all the way to the DIMM. You can, there's a point where it's accepted by the memory subsystem where you can say it's persistent. And the hardware guarantees it. The hardware, if it loses power, it has enough stored energy to flush that little bit of extra queuing there. But what I really want is the big red box. I want it so that you just do a store and say, no, it's persistent. But to do that, I would have to do the same thing with those CPU caches. I would have to make them flush on fail. Well, they're huge. They're megabytes. They're many megabytes. So now I've got to go down to the auto parts store and buy a car battery and hook it up to my computer to have enough stored energy to do this. And that's not something we thought we could require of every server out there. So right now, today, the small red box is required. The big red box is something you could build if you control your own platform. And so part of the programming model, part of the way that you program persistent memory is when you start up, you look to see whether you're in the mode of the small red box or the big red box. And you decide, do I need to be worried about flushing the CPU caches or not? And wouldn't it be nice if there was some sort of, I don't know, library that did all that for you? Probably. Okay, so what's the current state of the ecosystem for getting all this to work together? For the detection of whether the DIMMs are plugged into the machine, we made changes to ACPI. We made the changes in ACPI 6.0. We're up to 6.2 now. So the changes are actually fairly mature. And they identify the NVDIMMs that are in the system, communicate them to the OS. That causes those drivers that I showed you to load. What are the persistent memory aware file systems? So on Linux, there are two of them that are currently upstream. That's ext4 and XFS. They both support that DAX option that I was talking about before. The reason I said it the way I said it, two of them that are upstream, is that there are at least two of them that are not upstream. And I'm hoping that we see even more of this, you know, how the Linux development community, they love file systems. They like to have multiple choices of file systems. And I think that's actually pretty cool. So I expect to see some really interesting research going on there. Look up the papers on Nova, for example, and I think you'll find there's some very cool stuff happening there. But it's also nice to have these sort of weathered file systems that have been through a lot of production in all these years. They have this feature. Just to be really transparent, though, I don't want you to think that everything's done, right? We have a guy, Dan Williams, who works at Intel, who's continually improving and refining the stuff in Linux. For example, because this is a crowd that knows a lot about RDMA, he's still working on making RDMA something that's safe from these file systems. And right now you have to use there's an alternate way that you get to persistent memory if you want to use RDMA for about another 1 or 2 Linux kernel releases till he gets his changes upstream. So I just want you to know that it is an ongoing thing, but coming soon. Windows, they have a persistent memory aware file system, NTFS. Again, it takes a DAX option. You can read all about it, both of these, just by searching for DAX online. Is it safe to just use those cache flushing instructions that I mentioned before from user space? So these instructions that I show on the right, CLWB, cache line write back, is that safe? Can you just do that? Or does the kernel need to know when you're flushing something to persistence? It is safe on Linux if you use a new flag that was introduced fairly recently called map_sync. And it is safe on Windows with their NTFS DAX implementation. Remote flush is something that we're going to talk about coming up here in the next talk, so I won't go there. Deep flush is something that is trying to get the store into the smallest possible failure domain possible. And if you're interested in some of these other flushes and all the research we're going to do on these different types of flushes in our SNIA twig, come to the BOF tomorrow at 1 o'clock, and we're going to have a SNIA NVM Programming twig BOF, where we'll talk about this in more detail. So what about transactions and allocators? Well, I mentioned that it'd be nice to have some libraries. We put together some. They're called the Persistent Memory Developer Kit, PMDK. And the PMDK is at that URL. It's the coolest part of our entire project. pmem.io is the URL. And I'll talk about that more in a second. But I do want to mention that virtually all the virtualization technologies also plan on exposing persistent memory using that same model that I pointed to before. In other words, in a guest, you can get direct load store access to persistent memory. The changes in KVM are already upstream to do this. The changes in Zen are under evaluation right now. And the other hypervisors, I can't speak for them, but they have publicly said that changes are underway. Okay, so one last thing about the libraries. Go to the website if you want to learn about them. You can see where they fit into my stack. There's actually a menu of libraries. There's 10 of them. They do things like arbitrary transactions, begin, allocate, 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 make a bunch of changes, end, and either all of it happens or none of it happens in the face of failure. So even one of our libraries has a RDMA replication baked into it. It's just the first cut at it. It's active-passive, but it does actually work. A transaction is not complete until it's happened both locally and remotely. So that's worth looking at. Okay, so in summary, persistent memory technologies are emerging. Obviously, some of them are available soon, like this DIM here, since I'm still holding up a sample and not the product. But I think the capacity explosion is what makes this really exciting. And the ecosystem is actually pretty far along, amazingly far along. The existence of the current NVDIM products really helped us get a lot of stuff upstream, rather than having to wait until we shipped a DIM. Stay tuned for Tom's talk on this. I also just wanted to say that just recently, I think it was yesterday, we announced this alliance between this SNIA technical work group where we're working on the programming model and so on, and the OpenFabrics Alliance, where we're going to attack some of these issues more head-on together as a collaboration. There's some slideware bubbles and arrows about it, but you basically get the idea that we are not experts on things like networking and RDMA and that twig. We're experts on persistent memory. And so this is really a nice joining of two levels of expertise. And that's my talk. There you go. Any questions? Anybody want to know what it costs? That's usually the first question. I'm not going to answer it, but you could ask.
Are you giving some out?
Yes, I'm giving out pictures of the DIM, as many as you want. Okay, thank you.